Welcome! In this video, we'll tackle a classic and important problem in dynamic programming, the longest common subsequence. This problem is widely used to test your understanding of recursive strategies, memoization, and optimization. Let's dive in and explore different approaches to solve it. In this problem, we are tasked with finding the length of the longest common subsequence between two strings, text1 and text2. A subsequence is a sequence that can be derived from another string by deleting some or no characters while keeping the relative order of the remaining characters unchanged. For example, ACE is a subsequence of ABCDE because we can remove B and D without altering the order of A, C, and E. However, AEC is not a subsequence of ABCDE since the order of A, E, and C does not match the original string. A common subsequence, as the name suggests, is a subsequence that exists in both strings. If no common subsequence exists, the result should be 0. The input strings, text1 and text2, will have lengths between 1 and 1000, and both will consist of lowercase English letters. The output will simply be an integer representing the length of the longest common subsequence between the two strings. Let's begin with an example. Suppose text1 is ABCD and text2 is ACE. In this case, the longest common subsequence is ACE, which appears in both strings and has a length of 3. This means the output for this input is 3. This demonstrates how the characters of a subsequence can remain in the original order while some are omitted, as long as the relative order is preserved. Now, take another example where both text1 and text2 are ABC. Here, the entire string itself is the longest common subsequence, and its length is also 3. For the second example where both strings are ABC, the output is 3 because the strings are identical. Now, consider a different case where text1 is ABC and text2 is def. Here, no characters match between the two strings. As a result, there is no common subsequence, so the output is 0. This shows that the length of the longest common subsequence can vary significantly depending on the overlap between the two strings, ranging from the total length of one string to 0 if they are completely disjoint. When solving this problem, there are a few constraints and edge cases to keep in mind. First, both strings have lengths between 1 and 1000, and they only contain lowercase English letters. Edge cases include scenarios like completely disjoint strings, such as text1 equals ABC and text2 equals XYZ, where the result is 0 because there are no common characters. Another case is when both strings contain a single matching character, like text1 equals A and text2 equals A. Here, the result is 1 because the strings are identical and of length 1. If one string is empty, for example text1 equals ABC and text2 equals, then the result is 0 since an empty string has no subsequences. Finally, if the two strings are completely identical, like text1 equals ABCD and text2 equals ABCDE, the longest common subsequence is the entire string, and the result is the length of the string, which is 5. To solve the problem efficiently, especially given the constraints of string lengths up to 1000, we use a dynamic programming approach. We define a 2D DP table where dp, I, j, represents the length of the longest common subsequence between the first I characters of text1 and the first j characters of text2. This table allows us to systematically build up the solution by considering all possible substrings of the input strings. In the upcoming slides, we will explore this approach in detail and see how to implement it step by step. To solve the longest common subsequence problem, we first considered a brute force approach using recursion. The idea here is to generate all possible subsequences of one string and then check which of these subsequences are also present in the other string, while keeping track of the longest match. This is implemented using a recursive function that compares characters from both strings. If a pair of characters match, they are included in the subsequence, and the recursion proceeds to the next pair. If they don't match, the function explores two possibilities: skipping the current character in the first string or skipping the current character in the second string. However, this approach has exponential time complexity, 2 to the power of n asterisk 2 to the power of m, because it re-evaluates overlapping subproblems multiple times, making it highly inefficient for longer strings. This inefficiency is the main drawback of the brute force method. To address the inefficiency of the brute force approach, we turn to dynamic programming using a 2D table. Here, the intuition is to break the problem into smaller overlapping subproblems and store their intermediate results in a table to avoid redundant calculations. Specifically, we define a table where each cell, dp, I, j, represents the length of the longest common subsequence between the first I characters of text 1 and the first j characters of text 2. If the characters at the current indices match, the value in the cell is derived from the diagonal element, dp, I1, j1, plus 1. If the characters don't match, the value is the maximum of the left cell, dp, I, j1, and the top cell, dp, I1, j. This method has a time complexity of O, and *m, and a space complexity of O, and *m, as well. While efficient, the memory usage can be further optimized. This leads us to the space-optimized DP approach, which uses a rolling 1D array. In this method, instead of storing the entire 2D table, we only maintain the current and previous rows. By iteratively updating these arrays, we achieve the same result with reduced memory usage. Although this approach has the same time complexity, it reduces the space complexity to O, min, n, and m. However, it introduces slight implementation complexity and can be less intuitive to debug. Given these considerations, we selected the 2D dynamic programming approach as the primary solution. This method strikes a balance between efficiency, clarity, and ease of implementation. While the space-optimized version is more memory efficient, the 2D table approach is more straightforward to implement and debug, making it a practical choice in most scenarios unless there are strict memory constraints. The key insight here is recognizing that the problem exhibits overlapping subproblems and optimal substructure, which are hallmarks of problems suited for dynamic programming. The recursive approach, though conceptually simple, becomes infeasible for larger inputs due to its exponential time complexity. Additionally, understanding that the full 2D table isn't entirely necessary at all times leads to the space-optimized variant, where only the current and previous rows are maintained. These observations guided the choice of the 2D table approach as the most balanced solution. When comparing the trade-offs, the recursive approach, while conceptually simpler, is highly inefficient due to its exponential time complexity. On the other hand, the dynamic programming methods provide significant improvements in performance. Between the 2D DP and the space-optimized DP, the latter reduces memory usage but comes with slightly higher implementation complexity. For most use cases, the 2D table approach offers a better balance between simplicity and performance, making it the preferred general-purpose solution. It achieves optimal time complexity, is straightforward to implement, and avoids the exponential growth issues of recursion. However, in scenarios where memory is a critical constraint, the space-optimized DP approach could serve as an alternative. Overall, the 2D DP solution stands out as the most practical choice for solving this problem in a clear and efficient manner. To solve the longest common subsequence problem with dynamic programming, we start by clearly defining the problem. You are given two strings, x and y, with lengths m and n, respectively. Your goal is to determine the length of the longest subsequence that is common to both strings. A subsequence maintains the relative order of characters but may skip some elements. Next, we design the dynamic programming table. This table, dp, is a 2D array where dp, I, j, represents the length of the LCS of the first I characters from x and the first j characters from y. The table's dimensions will be m plus 1 by n plus 1, as we must include a base case for when one or both strings are empty. For these base cases, if either I equals 0 or j equals 0, the LCS length is 0 because an empty string has no common characters. Thus, we initialize all values in the first row and first column of the DP table to 0. Now, let's establish the recursive relation that helps us fill the DP table. For each pair of characters, x, I1, and y, j1, we compute dp, I, j. If these characters match, they contribute to the LCS, so dp, I, j, is 1 plus the value at dp, I1, j1, which represents the LCS of the prefixes excluding the matching characters. If the characters don't match, then we consider the maximum LCS length by either excluding the current character from x or from y. This is captured by taking the maximum of dp, I1, j, and dp, I, j1. With this recurrence, we iteratively compute the values for all cells in the table, row by row and column by column. By the time we reach dp, m, n, we have the length of the LCS. Additionally, if we want the LCS sequence itself, we can backtrack through the table starting at dp, m, n. When the characters match, we include that character in the LCS and move diagonally up left in the table. Otherwise, we move in the direction of the larger value, either up or left. Reversing the collected characters gives the final LCS in correct order. This problem is a great example of optimal substructure, where the solution to the LCS of x and y depends on the solutions to their smaller prefixes. This property allows us to break the problem into smaller overlapping subproblems, making it an ideal candidate for dynamic programming. Using this approach avoids the inefficiency of brute force, which would involve generating all subsequences of one string and comparing them, leading to exponential time complexity. By storing results of overlapping subproblems in the DP table, we reduce the complexity to O, m times n. Further, space optimization is possible because each cell in the DP table depends only on the current and previous rows. This allows us to reduce space complexity to O, min, m, n, by maintaining two rolling arrays instead of the full DP table. It's also important to consider edge cases, such as when one or both strings are empty, where the LCS length is naturally 0. Similarly, if the strings have no common characters, the LCS length is 0, and the algorithm handles duplicate characters correctly by relying on the recursive relation. The core data structure in this solution is the 2D DP table, which stores the intermediate results of subproblems. The size of this table is m plus 1 by n plus 1, corresponding to the lengths of the input strings plus 1. This table allows us to efficiently compute the LCS length by breaking the problem into overlapping subproblems and solving them iteratively. If we also want to retrieve the LCS sequence itself, we use additional space to maintain a list of common characters during the backtracking process. For space optimization, instead of storing the entire table, we can use two rolling 1D arrays to keep track of only the current and previous rows of the DP table. This reduces the space requirement to O, min, m, n, while still allowing us to compute the LCS length. The main operations in this algorithm are filling the DP table and optionally backtracking to construct the LCS sequence. For the DP table, each cell DP, I, j, is computed in constant time, resulting in a time complexity of O, m times n, for the entire table. Backtracking through the table to construct the LCS sequence, if needed, takes O, m plus n, time since we trace through at most one row and one column. In terms of space complexity, the full DP table requires O, m times n, space. However, with the space optimization using rolling arrays, we can reduce this to O, min, m, n, when only the LCS length is required. These optimizations make the dynamic programming approach both time and space efficient for solving the longest common subsequence problem. This implementation solves LeetCode problem number 1143, longest common subsequence, using a dynamic programming approach. Here's a detailed explanation of the code. 1. Initialization. The function longest common subsequence takes two input strings, text1 and text2. First, we determine the lengths of these strings, m and n, which will help us define the dimensions of the dynamic programming, DP, table. 2. DP table setup. A 2D list DP of size, m plus 1 x, n plus 1, is initialized with zeros. The extra row and column, indexed at 0, simplified boundary conditions by representing empty substrings of text1 and text2. 3. Filling the DP table. We iterate over both strings using nested loops. For each character pair, I, j. If the characters text1, I1, and text2, j1, match, we update DP, I, j, to DP, I1, j1, plus 1, which means we've extended the common subsequence by one character. Otherwise, if the characters don't match, we take the maximum value between DP, I1, j, ignoring the current character of text1, and DP, I, j1, ignoring the current character of text2. For result extraction, the value in DP, m, n, the bottom right corner of the table represents the length of the longest common subsequence between text1 and text2. This approach has a time complexity of O, m asterisk n, where m and n are the lengths of the two strings, and a space complexity of O, m asterisk n, due to the DP table. The logic ensures that all edge cases, such as empty strings, are correctly handled, as the DP table is initialized with zeros. This solution is both efficient and easy to understand, making it a robust choice for solving the LCS problem. This is the Java implementation for the LeetCode problem longest common subsequence. The logic closely follows the Python solution, with adjustments for Java syntax. Key differences include the use of Java's charat method to access characters and the math.max utility method for comparisons. The solution uses a 2D int array for dynamic programming, where dp(i,j) stores the length of the LCS for the substrings up to indices i1 and j1. The final result is stored in dp(m,n), representing the longest common subsequence length of the two input strings. To solve the longest common subsequence problem, the goal is to determine the length of the longest subsequence shared between two strings, text1 and text2. A subsequence is formed by deleting 0 or more characters from a string without altering the order of the remaining characters. For example, given text1 equals ABCDE and text2 equals ACE, we want to find the longest sequence of characters that appear in both strings in the same order. We begin by setting up a dynamic programming table, or DP table, to store intermediate results. If m is the length of text1 and n is the length of text2, we initialize a m+1 in fix n+1 table filled with zeros. This table will help us systematically compute the length of the LCS by breaking the problem into smaller subproblems. The next step is to fill the DP table. We iterate over each character of text1 and text2 using two loops, one for I from 1 to m and another for j from 1 to n. At each step, we compare the characters text1, I1, and text2, j1. If the characters match, this means they can contribute to the LCS, so we set dp I, j equals dp I1, j1, plus 1. For instance, when I equals 1 and j equals 1, both characters are a, so we update dp 1, 1 to 1. If the characters don't match, the LCS for this position must be the maximum of the LCS values from excluding either the current character of text1 or text2. For example, with I equals 1 and j equals 2, text1, 0, equals it and text2, 1, equals c do not match, so we set dp 1, 2 to the maximum of dp 0, 2, and dp 1, 1, which is 1. This process is repeated for all I and j. After completing the iterations for all characters, the DP table is filled with the results of the subproblems. The final DP table for text1 equals ABCD and text2 equals ACE looks like this: 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 2, 2, 0, 1, 2, 2, 0, 1, 2, 3. The value in the bottom right corner of the table, DP 5, 3, gives us the length of the LCS, which is 3. This means the longest subsequence shared by both strings is of length 3. For example, the LCS itself is ACE. Now, let's examine another example to further solidify our understanding of the approach. In our second example, we take text1 equals ABC and text2 equals def. Just like before, we start by initializing a DP table of size, m+1 ajax, n+1, filled with zeros, where m equals 3 and n equals 3. The DP table initially appears as 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. As we proceed to fill the table, we find that no characters in text1 match any characters in text2. For every pair of indices I and j, the value of dp, I, j, is determined by taking the maximum of the values directly above or to the left in the table. Since there are no matches, all the cells remain 0 throughout the computation. The final DP table ends up being identical to the initial 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. With the DP table filled, we can observe that the value in the bottom right corner, dp 3, 3, is 0. This indicates that there is no common subsequence between text1 and text2. Thus, the length of the LCS is 0. This example highlights how the algorithm handles cases where no characters are shared between the two strings. By systematically filling the DP table, we confirm that the result is correct. Now, let's consider one final example where the two strings are identical to see how the algorithm performs in such cases. In the third example, we consider text1 equals ABC and text2 equals ABC. After initializing a DP table of size, m+1 in fix, n+1, with zeros, we begin filling it by comparing characters of the two strings. Since the strings are identical, every character at position I in text1 matches the character at position j in text2. Each match allows us to increment the diagonal value, so dp, I, j, equals dp, I1, j1, plus 1. The final DP table is 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 2, 2, 0, 1, 2, 3. The value in the bottom right corner, DP, 3, 3, is 3, which represents the length of the LCS. Since the strings are identical, the LCS is the entire string ABC, and its length matches the length of the strings. This example demonstrates the optimal scenario for the LCS algorithm, where every character contributes to the subsequence. The time complexity of the solution is determined by the size of the two input strings, text1 and text2. Here, m and n represent their respective lengths. To compute the longest common subsequence, we iterate through each character of text1 using an outer loop, which accounts for m iterations. For every character in text1, we then iterate through all characters of text2 with an inner loop, contributing n iterations. This means that each combination of indices, I, j, is visited exactly once, resulting in a total of m*n operations. At each of these steps, we perform constant time operations such as comparing characters or updating the table based on previously computed values. When we combine these contributions, the overall time complexity is m*n for all operations in the algorithm. The space complexity of the solution arises from the dynamic programming table, which stores intermediate results. This table has dimensions m+1 n+1, meaning it requires space for m+1 n+1 entries. In big O terms, this is simplified to m*n. Beyond the table, the algorithm uses a few variables, such as loop indices and constants, which take up negligible space, or O1. If the problem only requires the length of the longest common subsequence and not the subsequence itself, the space usage can be optimized. Instead of storing the entire table, we can keep only 2 rows at a time, as each row depends solely on the current and the previous row. This optimization reduces the space complexity to n, making the algorithm more efficient in terms of memory usage. A brute force approach to solving the longest common subsequence problem would involve generating all possible subsequences for both strings and comparing them to find the longest match. However, this becomes computationally infeasible as the number of subsequences grows exponentially. Specifically, there are 2*m subsequences for text1 and 2*n for text2, so comparing all pairs results in a time complexity of 2 to the power of m*, 2 to the power of n. In contrast, the dynamic programming approach reduces this to m*n by breaking the problem into smaller subproblems and storing intermediate results. This eliminates redundant calculations and makes the solution practical for larger inputs. Importantly, whether the input strings have many common characters, few, or none at all, the complexities remain consistent at m*n in all cases. This demonstrates the efficiency and robustness of the dynamic programming approach. To mathematically validate the big O notation for this algorithm, we consider the total number of operations required. The dynamic programming table has m*n cells, and each cell is updated in constant time. Since there are no nested operations beyond the 2 main loops that populate the table, the total computational effort is proportional to the size of the table itself. This confirms that the time complexity is bounded by m*n. Similarly, the space complexity is proportional to the size of the table for storing results, which is also m*n. With no additional nested structures or higher-order operations, both the time and space complexities are conclusively m*n. When working with the longest common subsequence problem, there are several common mistakes to watch out for. First, it's important not to confuse subsequences with substrings. Substrings are contiguous, while subsequences simply maintain the relative order of elements and don't need to be consecutive. Misunderstanding this distinction can lead to incorrect solutions. Next, in recursive implementations, an incorrect or missing base case is another frequent issue. For example, forgetting to return 0 when one of the strings is empty can result in infinite recursion or incorrect results. Always handle edge cases like empty strings properly. Another challenge arises from using a naive recursive approach without memoization. This leads to exponential time complexity, which becomes impractical for larger inputs. Incorporating memoization is essential to avoid redundant computations and improve efficiency. Lastly, improper index handling in loops is a common pitfall. Off-by-one errors while iterating through strings or accessing dynamic programming arrays can disrupt your solution. Carefully initializing and updating indices is critical to avoid such errors. Another area to be mindful of is the time and space complexity of the dynamic programming approach. Some developers assume that dynamic programming is always space-intensive because of the need for a full DP matrix, which requires O(m*n) space. However, space can often be reduced to O(n) using optimized row-wise storage techniques. Now, let's discuss how this problem often appears in interviews. Recognizing the longest common subsequence as a classic dynamic programming problem is key, but it's also important to understand its variations, such as the longest palindromic subsequence or edit distance. These are frequently tested in technical interviews. You should also be prepared to explain optimization strategies, like reducing space complexity using a rolling array. Testing edge cases such as empty strings, completely non-overlapping strings, or one-character inputs is crucial, as these scenarios are often used to validate solutions. Finally, while iterative solutions are generally preferred in interviews because of their clarity, a solid grasp of the recursive formulation can deepen your understanding of the problem and may come in handy for follow-up questions. This problem is closely related to several others that build on similar concepts. For example, the longest palindromic subsequence problem or the delete operation for two strings are natural extensions of the longest common subsequence. Other examples include the minimum ASCII delete sum for two strings in determining if one string is a subsequence of another. Understanding these related problems can help you recognize patterns and transferable techniques. As for alternative approaches, the recursive solution with memoization is simple to implement but can be space-intensive because of the recursion stack and memo table, making it more suitable for smaller inputs. The dynamic programming approach using a full matrix is robust and clear, with O(m*n) time and space complexity, but it may not be the best choice for very large inputs. For space-constrained environments, the space-optimized dynamic programming approach is a better choice, as it reduces space complexity to O(n) by using a rolling array. While slightly more complex to implement, this method is an essential tool for solving LCS efficiently. By mastering these techniques and understanding how to avoid common pitfalls, you'll be well prepared to tackle both LCS and its variations in technical interviews. Great job! To summarize, we learned how to solve the longest common subsequence problem using dynamic programming. We also discussed its time and space complexities and key takeaways for real-world applications and interviews. Don't forget to like and subscribe for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!